Okay, so this chapter is about oscillations, and we will talk about a very special kind of oscillations. It's called a simple harmonic motion. Okay. And if you make a living as an engineer, this will never leave you. Okay. It'll be with you the rest of your life. So let me illustrate this. So here is a simple harmonic motion. Okay. This mass attached to a spring is executing simple harmonic motion. Okay. That is one oscillation. Okay. The time for one oscillation is called a period. Okay. You can see this oscillation. It's got a small amplitude. Okay. So you can time how long it takes for one oscillation, okay, and get its period. Or you can do this. Now the oscillation has a larger amplitude. Is this period longer?
No.
No. Okay, so this is the neat thing about it. Okay, the period is independent of the amplitude. Okay, so that's the hallmark of simple harmonic motion. Okay, now let's do a couple of obvious things. Let's answer a couple of obvious questions. What if I make the mass heavier? What will happen to the period?
Period would be the same, amplitude would increase.
Okay, so if you make the mass heavier, the period would increase as well. Okay? All right, what if I make this spring stiffer? Shorter period. Okay, so those are two obvious things. All right, so we'll learn all of that. Okay, so this motion is called simple harmonic motion. That's what we're going to study. Okay, so here's the deal. So here's the mass attached to the spring. There's the equilibrium position of the mass. Okay, now if I pull the mass to the right, what will happen? What will the spring do? It'll pull back in this direction. Okay, it's pulling it back and trying to bring it back to the equilibrium position. Okay, if I compress the spring, what is the spring trying to do? Again, bring it back to the equilibrium position. Okay, so the force that the spring exerts when the system is disturbed is a restoring force. Okay, it's a restoring force because the forces that come into play are trying to restore the system back to its equilibrium position. Okay. Here's a counterexample. So let's say you have a hill, and I put a marble on top of the hill. That's an equilibrium. But if I disturb it from its equilibrium position, the forces that come into play will take it up further away from equilibrium. Okay? And so those forces are not restoring forces. This force is a restoring force. Okay? You learned about potential energy. So the potential energy of this guy is on a peak. The potential energy of this guy is like that. Okay? And this is the equilibrium position. So local minima of potential energy give you restoring forces. Around local minima, you have restoring forces. Around local maxima, you have forces that take you away from equilibrium. Okay. But don't worry about all of that. Okay, so the forces that come into play are restoring forces. Now, so for simple harmonic motion, you have to have simple restoring forces, and in addition, you need to have this following. Okay, the restoring force needs to be proportional to the displacement. Okay. This is a very hard problem. This is a much harder problem to solve. Okay? So what we'll be doing is we'll be looking at restoring forces that are proportional to the displacement. Okay? We'll keep life simple. Okay. And for most oscillations, that's good enough. Okay. So for this oscillation where the disturbance is small from the equilibrium, when the amplitude of oscillation is small from the equilibrium, that's good enough. You know, that kind of analysis. You can analyze bridges vibrating this way using this kind of model, buildings vibrating, and so on. Yeah. All right, so that's what we're going to study. All right, now that we know the force acting on the system, what is this? That's the force acting on this mass. Okay, and you're very friendly with Mr. Newton. So, what did Mr. Newton tell you? Force acting on an object is equal to the mass times acceleration of the object. Okay? The acceleration of the object is the second time derivative of the position of the object. Okay? So, acceleration is d square x by dt square is equal to k over m times x. What is k?
The spring constant.
Yep. Is it a positive number or a negative number? It's positive number. The spring constant is always a positive. The mass is always a positive number. K over m is a positive number. Okay. So just so nobody gets confused, we'll write it as omega squared. Okay. Omega squared is a positive number as long as omega is real. Okay. So, all right, we'll call it omega squared. Okay. So, and there is omega squared, and we'll bring it to this side. And what is this? What is this? This is a differential equation governing the behavior of the position of the mass. So d squared by dt squared xt omega squared xt equal to 0. There you go. What this equation is saying is, okay, you hit this thing with a hammer, do whatever you want to do to it, and the motion it executes, that position as a function of time satisfies this differential equation. All right, so you've learned a very important thing, and this will track you as an engineer the rest of your life. Okay, here's what's going on. Here is a system. We put a physics principle in, and the behavior, to model the behavior of the system, we got a mathematical equation. This mathematical equation is modeling the behavior of this guy. And this mathematical model in general is a differential equation. Okay? So that's one of the reasons why you study differential equations. Okay? So this is a very simple system, and this is where you get introduced to differential equation. But you can apply this to any complicated system. You can apply it to a predator-prey system. So here is a savanna, and you put a bunch of here is a savanna. You put a bunch of lions, and you put a bunch of wildebeest. Okay, so let's say this is the population of lions as a function of time. This is the population of wildebeest as a function of time. If this is too large, what will happen?
Population of wildebeest will go down to nothing.
Yes, so if it's extremely large, this will go to 0. Okay, but let's say we don't want, you're in a regime where in nature it doesn't want to go to 0. Then this will start decreasing, so the wildebeest population comes up and all that. Okay, and so to describe the behavior, the dynamical behavior of this population, you'll come up with a couple differential equations. All right. All right. So again, so here's what we've learned. So you have a system. You want to study the system. Okay. You put whatever principle that goes in here. So we are doing physics. Okay. And then you'll come up with an equation governing the behavior of that system. And you solve the differential equation. You come up with solutions. and you go test it out in real life and see if the real life system actually behaves that way. Well, why do we want to do this? Why not just set this up in lab and study it?
So we can apply it to theoretical or impossible
So
simulate.
this is much easier. Okay, this is much harder. And then, if this does not agree with this, you can figure out the reasons why, figure out new rules or laws that'll describe the behavior correctly. Okay? So this is much easier for analysis. All right, anyway, here is a differential equation that describes the behavior of this system. And then when you take your differential equation class, they'll show you how to solve this equation. Okay? What we mean by solving this equation is we want to find out functions that satisfy this differential equation. Okay? Well, what does this function tell you? What is that function telling you? What is that x of t? I'm sorry? That's right. It's telling you the position of. That's what we were interested in. Okay? So here's a solution. You can plug this back in there, the equation, and make sure that it does satisfy the equation. So you can plug this back in here. And you can verify that this will indeed satisfy this equation. Okay. Now let me point out a couple of things about the solution. Okay, so this is the solution we're looking at. All right. What is this A? That A is not in this equation. Look at this constant phi. That is not in this differential equation. All right. So let me get back to this diagram. All right. I pull this aside and let go. Where all can I pull it and let go of it? How many different positions can I pull it and let go of it?
Infinite number.
Infinite number. I pull it and then I give it a little push. How many different kinds of pushes can I give? An infinite number of pushes. Okay. So you see, depending on those initial conditions, the particular motion will be different. Okay. So if I give it a push 10 meters a second, it'll execute a certain motion. If I give a 5 meter push per second, it'll execute another particular motion. These two constants determine those initial conditions. Yep. Those two constants, the initial conditions determine those two constants. Okay. So here's the rule. If you have a second order differential equation, you will have two constants that are determined by initial conditions. If you have a third order differential equation, how many constants will you have? Three. All right. If you have a fifth order differential equation, 5. All right. This is called a linear differential equation. Okay. So this is the order of the derivative, and every term is linear. So this becomes a hard problem to solve. This becomes a hard problem to solve. Non-linear differential equations become hard. Okay. So this is, the terminology is, this is a second order linear differential equation. All right, so we learn differential equations because when we come up with a mathematical model to describe a system, it's generally a differential equation. Again, you'll learn techniques to solve these equations. And once you have solutions, so here we have a solution, and we want to see if our system actually behaves that way. Okay? And here's an illustration of that. what you could do is, so what is this? This is a sine and or a cosine function. So the solutions are sine and cosine functions. Okay. So let's see if the real world actually behaves that way. Okay. So you can take a mass, attach it to a spring, stick a pen on it. Okay. And the way we will simulate time is we'll get a paper scrolling at constant speed. That will simulate time. Okay? And then, well, x is being measured in this direction. We'll set this in oscillation. And what you'll find is you'll get a sine cosine curve. Okay? So the real world indeed behaves like that. So what does that mean? This equation was correct. Yep. All right. What if we did this? Where are you going? All right. I was just giving you a hard time. I messed with her, didn't I? All right, now if we do it for this system, I stick a pen here, and I make the paper go the same way. You'll find that now the trace will be like that. Okay, let's see if I have a diagram of the trace. Yeah, there's the diagram, the blue line. It'll be like that. That doesn't agree with that solution, right? So that means this is not the right equation for it. This is not the right mathematical model to describe this system. It turns out that you need this extra term. Okay, so that's the new differential equation describing that system. Okay. All right, so you guys understand all of that. All right, so we've come up with the solution. That is, we have the position of the mass as a function of time. Okay. All right, so again, once you have the solution, now you can using your tools, you can go running. Okay, you can calculate the velocity of the mass as a function of time. You just take the time derivative of that. Time derivative of that is the velocity. Time derivative of the velocity is the acceleration. Okay. So there is the amplitude of the velocity. There is the amplitude of the acceleration. Okay. Omega is called the angular frequency. Okay. And so A is the amplitude of motion. Omega is the angular frequency. Phi is the initial phase. That's the term. A and phi are determined uniquely by the position and velocity of the object at t equal to 0. So they are determined by the initial conditions will determine that. Okay? Or those guys determine the particular solutions. Okay? So again, this is called a simple harmonic motion. What is needed for you to have a simple harmonic motion? What are the two things you need? What are the two ingredients that go into making this cake?
The restoring force is equal to the displacement.
Very good, my friend. The restoring force is proportional to the displacement. Very good. Okay. So this is you need to have a restoring force, and the restoring force needs to be that. Okay. This will not give you a simple harmonic motion. All right. And that's a much harder problem to solve. All right. All right, so here's another amazing thing. So what we have shown you is this guy. We attached a mass to a spring. We studied the system. Okay? Now let's look at some other systems. I'm going to come back to these slides and stuff like that. So here is the system we studied. How about this guy? What is this? This guy is, a disk, a uniform disk. You attach it to a metal wire and you can twist it and it'll oscillate. Okay, so you twist it and it'll oscillate back and forth. This is called a torsional pendulum. Okay. How about this guy? This is called a simple pendulum. You just hang a heavy mass from a light string, and if you pull it to the side and let go, it'll oscillate. Okay. This is called a physical pendulum. Okay. So there is the center of mass of this object. You can take anything. You can take this bag and make a physical pendulum out of it. Okay. You nail it there. The center of mass is there. If you pull it to the side, it'll oscillate. This is a physical pendulum. Very different systems, right? They're all cousins. All their behavior is determined by this equation. Okay. All you have to have is, to measure the configuration of the system, you have to have the appropriate coordinate. For the mass attached to the spring, it was xt. For this physical pendulum, you want to measure the configuration using this angle theta. Theta is the angle between the line from the point of pivot point to the center of mass to the vertical. So when you come to the physical pendulum, you replace xt by theta t. The same equation is governing it. Omega square was for the mass attached to the spring, it was this. Omega square was k over m. For this guy, omega square will be mgd over I. I is the moment of inertia of this object about that axis, okay? And m is the weight, mg is the weight of the object, and d is that distance, and so on. Okay. For this guy, omega square is g over L, theta is that, and again, d square, theta t. So you see the importance of studying a differential equation? Okay. You study one equation, and how many different systems did you get to describe? 100 million. All right, I was just exaggerating, but you describe many, many systems. Okay. All right, so coming back to our simple harmonic motion, there is the solution, there is the velocity, and there is the acceleration. Okay. And this did illustrate that the real world system did behave as predicted. Okay. There is the period. What is the period again?
Time for one full oscillation.
Time for one full oscillation. Okay. And the period is 2 pi m divided by k, the spring constant. And again, the neat thing about this period is, see, there is no amplitude information. The time for this oscillation is the same as the time for this oscillation. Okay? So if the amplitude increases, it compensates and goes faster, okay? So that the period is the same. Frequency is the inverse of the period. It's the number of oscillations it does in unit time per second. Okay? And so that's frequency. All right. So again, for simple harmonic motion, what did the two ingredients you needed were? You needed a restoring force, and that the restoring force was proportional to the displacement. Okay, how much have you disturbed the system from its equilibrium position? Okay. There's the equation of motion. Okay, or there's the equation for the coordinate of the mass attached to the spring. Okay. There's the solution Okay. And again, this was a second order linear differential equation. Since it was second order, you had these two unknown constants that determined the particular solution. Okay. So let's go back and draw that diagram again. So there's the equilibrium position. I'm going to pull it to the side and let go. Okay. So I'm not giving it any initial velocity, I'm going to let go. For this initial condition, A will be equal to that and phi will be 0. Okay. So phi is 0 at t equal to 0. This will be 0, and cosine of 0 is 1. So the object will be there. Okay, so I pulled it aside and let go. Now what will happen? I'm sorry? It'll start oscillating. Okay, and it'll go back and forth like that. How long will it oscillate?
Assuming no friction, no losses to heat
Mm-hmm.
forever.
Forever. Okay, so that's right. Okay. When is it going the fastest?
At the equilibrium point.
At the equilibrium point. And that's how fast it's going. Okay. When it's going in that direction, the velocity is negative. When it's going in that direction, the velocity is positive. And so the sign will tell you. Okay. So when it's going to the left, the velocity will be negative, and when it's going to the right, the velocity will be positive. Okay. So think about this one before you answer it. So velocity is the greatest, the speed is the greatest at the equilibrium point. When is the acceleration greatest?
At the amplitudes.
At the amplitudes. Very good, very good. So here's what our friend figured out. Acceleration is greatest when the force is greatest. The force is greatest when the x is greatest. So when you're the furthest, that's when the acceleration is greatest. Okay? All right, now we'll talk about the energy. So when it's oscillating, when it's moving, it has kinetic energy. And you know, when the spring is stretched or compressed, you have spring potential energy. Okay? So here's the kinetic energy, 1/2 mv square, and you have an expression for v there. Okay, we're going to substitute that for v. You put that for v and you get this expression. Here is the potential energy, 1/2 kx square. X is the position of the mass. We'll put this expression in there. Yeah, you get that. You see sine squared theta, cosine squared theta. If you add the two, you get 1. All right. So let's add these two, and it turns out that those two add up to 1, and the common factor is 1/2 ka squared. The coefficient is 1/2 ka squared. So the total energy, which is kinetic energy plus potential energy, is 1/2 ka squared. Okay. No matter where the object is, its energy is constant and it's equal to that. Okay. So the potential energy plus kinetic energy of this oscillation, the total energy is 1/2 ka squared. Again, when is this true? When there's no friction. Okay. And when there's friction, some of this energy is being converted to heat every oscillation. And then what will happen? You saw that. So when we added friction, this is what happened. The oscillation died. Okay, mechanical energy was being converted to heat. All right. Okay, so there's the maximum velocity or the maximum speed okay, which happens at the equilibrium, and there's the maximum acceleration, which happens at the extreme points. Okay. All right, what does this expression give you? What is this? Is that equation talking to you? What are we? What did these guys refer to? We're still talking about this. So we're talking about the velocity of this guy and the position of this guy. So what this expression is giving you is the velocity of that mass as a function of position. Okay. At the extreme position, what is the velocity of this guy?
0.
0. So if you put x equal to a, v will be 0. When is the velocity maximum?
At the equilibrium.
At the equilibrium position. When you put x equal to 0, the velocity is maximum. Okay. So this guy is giving you the velocity of the mass as a function of position. Yeah. And the plus or minus telling you plus is when it's going to the right, minus is when it's going to the left. Okay. Yep.
Would you be able to figure that out just looking at the equations, or do you need more information?
What do you mean?
You know, the direction of the block.
Yeah, just the equation. That's, well, and the assumption, well, assuming this is, you chose this to be positive and this to be negative. If you chose that to be positive and that to be negative, that's, the equation is telling you that as well. Well, the equation is not telling you your initial choice. All right, so we have all the tools now. Now we're going to apply it to a different system. Okay, so this is a torsional pendulum. Again, here's a disc attached to a stiff wire. If you attach the disc to a cooked noodle, will it oscillate?
Yeah.
No, it won't oscillate. There, the kappa is 0. Okay, the torsion constant will be 0. All right, so again, the torque is, so in this, the relevant configuration, so for this guy, for the mass attached to the spring, the relevant coordinate was x, this distance, to measure its disturbance from the equilibrium. For this guy, what you want is to measure this angle as you're twisting it. Okay, so this is the equilibrium position and the angle from the equilibrium position. Okay, so the restoring torque again is proportional to the displacement. Okay. And torque is I times d. Torque is I times alpha. This is again Newton's second law, and we're applying that. And again, torsion constant is positive, moment of inertia of this disk about that axis is positive. So we'll call it omega square. Okay. Kappa, the torsion constant, divided by I is omega square. And again, we'll bring that to this side, and you have the same exact differential equation. For the mass attached to the spring, it was dxt dt square plus omega square xt equal to 0. For this torsional pendulum, it's that. Okay, x got replaced, xt got replaced by theta t. But the equation is exactly the same. Okay. All right, so there's the solution again. Yep. Again, notice this is a second order linear differential equation, and how many constants will be there that are determined by initial conditions? 2. So there's the one constant and there's the other constant. Okay. Omega square is that. The period is I over kappa. Greater the moment of inertia, greater the period. Stiffer the spring, okay, lower the period. So a steel string, a steel wire will give you a lower period than an aluminum wire. Okay, so that's what that is telling me. You guys following this? Am I going too fast? You guys understanding this? All right. And now we'll do the simple pendulum. All right, so you attach a small heavy mass to a light string. That's what the simple pendulum is. The length of the pendulum is from the point of suspension to the center of mass of this object. Okay. If you pull this to the side, here's the weight of the object and here's the tension on the object. Tension in the string. Those are the only two forces acting on this object. Okay. There's the component of the weight that is balancing the tension. And there's the component of the weight that is unbalanced, which will make it accelerate, which will make it go back and forth. And that is the restoring force. This is the restoring force. Again, you have to have a coordinate to measure the configuration of the system. And this is the coordinate we use to measure the configuration of the system. Okay? So, that's what we are interested in. Yeah. No matter what you do and you let go, what we want to know is what is the angular position of the pendulum as a function of time. Okay. So again, we'll talk to Mr. Newton and see what he tells us. Okay. So there is the restoring force, there is the force, okay, and that is equal to mass times the acceleration. And his position is measured as S from the equilibrium position. Okay, so d square S by dt square. But this arc length is equal to L times theta, is L times theta. L, of course, is not changing, L is constant, so it's d square theta by dt square. So let me, okay, so theta t is what we're interested in. So minus mg sine theta is ml d square theta. Okay, and you can check for small angles. Okay, so again, you can check this in your calculators. And theta, as long as you put them you're in a radian mode, is approximately equal to theta. So you can check it for 0.1, sine 0.1 in radian mode, you'll get about 0.1. Okay, so sine theta is approximately equal to theta. Okay, and again, G is positive, L is positive, so, yep.
Is this while ignoring air resistance?
I'm sorry?
Is this while ignoring air resistance?
Yeah, no air resistance, yeah. Friction, air resistance, and all those things we're still learning to walk. Okay, we're not going to enter a 100-meter race yet. Okay. Definitely not with Usain Bolt. All right, so we'll call that omega square. Omega square will be G over L. So again, d square theta t by dt square plus omega square theta t equal to 0. Exactly the same equation. Okay, so the behavior of this system is also described by the same differential equation. Okay, so this is the equation for simple harmonic motion. Okay. So this coordinate, okay, different system executing simple harmonic motion, the coordinate might be different, the configuration coordinate might be different for different systems. Okay. All right, so the period is 2 pi square root of L over G. Okay. So this gives you an idea for clocks. Depending on the length, you have the period. So if you have a period whose period is 2 seconds, you can use that for a clock, or 1 second, or whatever. Okay. So you can also use this to determine the acceleration due to gravity of the object you are on. So if you look at old films of the moon landing, one of the first things that Armstrong did was there was a pendulum attached to the lunar lander, and he set that in motion. So kids watching that on TV, they could they could measure the period, they were told the length, and they could calculate the acceleration due to gravity on the moon. Okay. All right, now we'll come to a physical pendulum. Okay. So what was the difference between a simple pendulum and a physical pendulum? A simple pendulum is a tiny mass attached to a long string. So the dimensions of this object are small compared to the length of the pendulum. In a physical pendulum, the mass is distributed all over. All right, so there's the pivot point, and there's the center of mass. Equilibrium would be center of mass is right below the pivot point. And you pull it to the side and it'll oscillate. Is there a time when it will not oscillate?
When the pivot point's on the center of mass.
There you go, very good. Okay, if the pivot point is on the center of mass, it won't oscillate. Okay? So the restoring torque is mg, the weight, times, and the torque about this point, there's the moment term, which is d sine theta. So the weight times d sine theta is the restoring torque. Okay? So there's the torque, which is I times d square, I times alpha. Okay, again, Mr. Newton tells us do this. Okay? And that's what we've done. This is the torque, I times alpha. Okay? And again, for small angles, sine theta is equal to theta. Okay? So you get the same differential equation, d squared theta by dt squared plus omega squared theta, where omega squared is mgd over I. Okay. So now we have studied four different systems. For the first one, for the mass attached to the spring, omega square was k over m. For the torsional pendulum, omega square was kappa over I. For the simple pendulum, it was G over L. Okay. And here's for the physical pendulum. Okay. Okay. So again, the period is 2 pi I mgd. Okay. Again, when will it not oscillate? When the pivot point is at the center of mass. D will be 0. If D is 0, you get an infinite period. Okay? It's not oscillating. So this kind of stuff, so your grandfather clock really has a physical pendulum. But here's another interesting point. See, your leg is a physical pendulum. There's the pivot point. Okay, you can put in the numbers. Half a period. Okay, you can calculate your normal gauge speed. Okay. All right, so we are studying simple harmonic motion. There's the equilibrium position. Okay. There's the mass. You let go, it'll oscillate back and forth. All right, so now we'll look at a different kind of motion, a circular motion. Okay. A uniform circular motion. Okay, so we'll have a object going in a circle at constant speed. Okay. Now we're going to do the following. We're going to project this thing. So we'll project this motion on this plane. So here is the shadow of this guy. As this guy goes in a circle, the shadow, what is the shadow doing? Going back and forth. This motion is exactly the same as that motion. All right, where is the shadow going the fastest? At the center. And the speed of the shadow at the center is equal to the speed of this guy. Okay. You could make a projection on this wall as well. So it turns out that uniform circular motion is a combination of two simple harmonic motions. Okay. You guys might remember from the chapter on gravity. Remember we had dug a hole through the center of the earth, a tunnel, and that was a simple harmonic motion. Okay. And that was related to the International Space Station motion, which is exactly that. Yeah. So the International Space Station is executing two simple harmonic motions. Yeah. It's a combination of two simple harmonic motions. All right, these slides illustrate that. I'm not going to go through the derivation. So here is a uniform circular motion. This point is going at constant speed. Of course, it's accelerating because the direction is changing. And this component of the velocity is equal to that velocity, which is the velocity of a mass attached to a spring. And this is the acceleration. This component of the acceleration equal to that, which is the acceleration of that mass attached to the spring. Okay. Okay, so till now, we were dealing with systems without friction. Of course, life is not so pleasant. Okay. Or life is not as simple. There's always friction. So let's learn how to handle friction. Okay. So here's a simple model. Now we'll put that mass attached to the spring in a fluid, and the fluid will provide friction. Okay. So which way does the friction act? Which way? Very good, my friend. So if the mass is moving in this direction, the friction will be in that direction. And when the mass is moving in that direction, friction will be in this direction. Okay. So now here is the simplest model. Okay. So friction force. In this case, this is the drag force. Here is a simple model. Friction will be proportional to the velocity. Okay. The faster you're going, the greater the friction force. What is this B telling you? That's a coefficient, it's a. So the B tells you whether you're in water or honey, or it's related to the viscosity of the fluid. Okay. So greater B is, greater the friction force. Okay, so there's the drag force. It's proportional to the velocity, and B is the damping coefficient. All right, so so now we have a new model. We're going to model friction. So we're going to model this system. Okay, so here's our system. Okay, what is it that we want? We want a mathematical model to describe the system. And what is that mathematical model going to be? It's probably good.
Differential equation.
It's going to be a differential equation. Okay, so how do we get from system to mathematical model? We put in a little physics. Okay. All right. And right now, our best friend is Mr. Newton. Okay. Mr. Newton told us that mass times acceleration of this object is the net force acting on the object. Well, what are the forces acting on the object? The spring force and the friction force. Okay. Here is the spring force, and here is the friction force. So that's the net force, and the net force is equal to mass times acceleration. So there is the physics that we put in there. And let's see if that'll spit out a differential equation. Okay. All right, this is mass times acceleration is that, okay. Again, this is xt is the position of this guy as a function of time. There's the acceleration minus kx minus b dx by dt. We'll bring all those terms on one side, and there is that. What was the equation without friction? Without friction, if you want, all you have to do is drop that term. Make b equal to 0, and you get the equation without friction. Okay? So if you learn to solve this, it's like if you learn how to run, you know, of course, you know how to walk. Okay? So walking is just making this guy 0. Okay? So there's the mathematical model describing this system. You solve this, that is, you get a solution like that, and you know how this guy behaves. All right, here is a solution. Okay, so there was the model without friction. And so this was d and omega square was. Okay, and the solution was xt was a cosine omega t plus phi. With friction present, the equation became m d square xt by dt square plus b dx by dt plus kx equal to 0. So this equation changed to that, and this solution, you see that part was still the same. It is just the amplitude got multiplied by this factor, an exponentially decaying factor. Okay, with friction present, what is happening?
The
And
amplitude is reducing every time.
energy is being converted to heat. Okay, mechanical energy is being converted to heat, so that is reflected in the fact that the amplitude is decreasing. Okay? So there, that's the amplitude is decreasing. And in addition, this, see, the oscillation frequency changes slightly. Okay, this is the oscillation frequency without friction. With friction present, it reduces. So if this water was in there, beaker was in there, there was a frequency, it would oscillate, let's say, 10 times a second. With the beaker present, with the liquid present, now it's oscillating 9 times a second, which makes sense. Okay. All right, so there you go. So depending on how much friction there is, if there's little friction, it'll oscillate, and the oscillation might go on for a while. If there's too much friction, it won't even come back to its original spot. Okay, well, it'll just come back to its original spot. And if there's too much friction, it won't even come back to its equilibrium position. Why do we care about all this? Well, see, here's a practical application. Let's say you're riding a motorbike and you hit a pothole. Okay, so you're on the flat road and you're going on a flat road, and then you hit a pothole, and you see your wheel will come down, and then when you come back, your wheel is oscillating. And you have a bumpy ride. You want to kill that oscillation as fast as possible. Okay, you don't want it oscillating like that. You want to kill it as fast as possible. Okay. So that's what shock absorbers do. They provide damping to kill vibrations. Okay. Now we'll talk about forced oscillation. Again, I know this is a long chapter, but it's very important, and you need to make sure you go home and review it again. Okay. And I don't want to stop in the middle here. I have a few more slides. So, okay, what is this title saying?
Forced oscillations.
Okay.
Applying external pressure to oscillate.
All right, so it is like, let's say a child is on a swing. You can get the child to oscillate, and if there is friction present, what will happen? Slow down, and the child starts crying. So what do? You push. That's forced oscillation. Okay, so you're going to apply an external force and see what happens. Okay. All right, we're experts now. Don't be looking at it like that. You can solve it. Okay. So what does Mr. Newton tell you? Newton is your friend. Net force is equal to mass times acceleration. Okay. What is net force? Net force is sum of all the forces. Okay. So there is mass times acceleration. What is this guy?
It's your spring coefficient.
That's the spring force exerted by the spring. What is this guy?
It's your dampening force.
That's your damping force, because that was because you were in the water. And there is the driving force. Okay, you're going to apply a force of amplitude F naught, and it's an oscillating force. It's like, when you're pushing the child, you're doing a periodic force. This is the driving frequency. Okay, and now this will be very important, so we'll keep track of that. Okay. Now this gets to be a little hard to solve, so what we'll do is we'll give you the solution. So here is the solution. Again, it'll have the same form. There's the amplitude. The amplitude is a function of the driving frequency and the natural frequency of oscillation of the system. Okay. The natural frequency is the frequency it would oscillate at if you weren't driving it. Look at this. The system is oscillating at the driven frequency, not at its natural frequency. It's oscillating at its driven frequency. We'll come back to this diagram in a second. All right, so here's this amplitude as a function of the driving frequency and its natural frequency. Here is this amplitude. Okay. There's the amplitude of the force, there's the mass attached, there's the driving frequency, natural frequency, and this term. Okay. And notice the amplitude is largest when the driving frequency matches a natural frequency. Then this term goes to 0, and A is maximum. Okay. Notice if smaller b is, greater A is. And that's what this graph shows you. Smaller b is, greater the amplitude, as the driving frequency matches a natural frequency. So So when the driving frequency matches the natural frequency, that is 1. And for small damping, you get large amplitude oscillations.
What is that unit for B? Like 140 Gs per second?
Okay, so B has units of, it is a force. So B times velocity, meters per second, is newtons. Newtons is kg, meters per second squared. So B has units of kg per second.
I guess that's grams in that image. Okay.
I'm sorry?
So for the sake of the graph, that's grams presented.
Oh, yeah. All right, so I gave you the SI units. Well, this is very important, and this is very important to know. Okay, so let's make sure we understand this. This is called resonance. When the driving frequency matches a natural frequency, this is 1. And you see, for small damping, you can have large amplitude oscillations. For large damping, you'll have small amplitude oscillations. Okay, so whenever you build large structures, as an engineer, all structures will have natural frequencies of oscillation. Okay, so if the wind blows and it's exerting a random external force, if the frequency at which this is exerting a force matches this frequency, then you can have large amplitude oscillations and the structure can crumble. If you have an earthquake, the ground shakes. This is driving that. If the driving frequency matches a natural frequency, the buildings can fall down. Okay. So to prevent large amplitude oscillations, you have to have damping in there. All these large structures have damping. So here's a building in Philadelphia. Okay. If the wind blows and gets the building shaking and the frequency matches the natural frequency, you might end up having large amplitude oscillations and the building might fall. So here's how they're providing damping. On the top here, there's a tank of water. Okay. As the building sways this way, the water still is back there. And then as this building sways back, that's when the water is going that way and it's providing friction. Okay. So all these tall structures have damping in them. So this is a 300,000 gallon reservoir. All right, I got to show you. So I'll show you a simulation in a second. Okay, so this is old news, but anyway. So an earthquake happened. Angular frequencies of the seismic wave that reached Mexico City were concentrated around 3 radians per second. 3 radians is half an oscillation per second. So the period was 2. The ground was shaking with a period of 2 seconds. Okay, so the frequency was 0.5 hertz, roughly 0.5 hertz. Okay, and if the natural frequency of the building matched this 0.5 hertz, okay, so this was 0.3 hertz, this was 0.1 hertz, this was 0.5 hertz. I'm just making these numbers up. Okay, this building was fine, this was fine, this guy fell down. Okay, the driving frequency matched his natural frequency and large amplitude oscillations were set up. Okay. And that building fell down. So let me show you. Okay, so that phenomenon is called Okay, so resonance is the phenomenon when a driving force, when the frequency of the driving force matches a natural frequency, you set up large amplitude oscillations. So here's what we're going to show you. So here's this mass attached to the spring. We're going to hold on to the spring, and we're going to pump energy into the spring by driving the spring. Okay. So you see now right now the driving frequency does not match the natural frequency of the system. So we'll start this. Okay, so nothing spectacular is happening. Okay, now what did I do? See, now the driving frequency closely matches the natural frequency. So I'm going to do the same thing. I'm holding on to the spring, and still my driving amplitude is still the same, except what is different now? This time the frequencies are matching. So imagine if this were a building or a bridge, it's goodbye baby for this guy. Okay. Now let me show you a real world example. Okay, so this was a simulation. Okay, so here's what was happening. So this bridge was built somewhere near Seattle. So this is a top view. There's the bridge, and there is the piers under the bridge, and the wind was blowing, and vortices would develop, and these vortices would break away at a frequency, let's say 10 times every 2 seconds or whatever. That frequency matched a natural frequency of this bridge. So it's like you're applying a force that matched the natural frequency of the bridge. And here's what happened. All right, we'll just...
We're standing up for our right to be lazy.
By sitting down.
And reclining back.
We work full-time and...
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only at 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
So you see, that bridge didn't even last 6 months. 35-mile-an-hour wind. This was in 1940. Okay? So you saw that in that tall building we had put damping in. Okay? In all structures nowadays you put damping. But so even though every engineer has been taught this, it still happens. They built a bridge, a walkway bridge across the Thames in London 10 years ago. And the first day, 2,000, 3,000 people walked across it. It set up these oscillations. Okay? And so they had to close it down for 2 years to fix it. You guys have heard of they won't let a battalion march across a bridge? I guess if their marching frequency matches the natural frequency of the bridge, you can collapse the bridge. Yep. All right, guys, so that finishes this chapter.